Welcome to Calculus. You might be a high schooler who's deciding to take AP Calc, or you might be a college student deciding your major, or you're just curious about Calc. You might be intimidated by the subject, and I can understand that. But this is what this video series is for. In this mathematical minimum series, basic concepts and ideas behind them will be carefully introduced. And after this video, you may realize that you could have come up with the same methods used in calc. You could have invented the core stuff of calculus yourself. Of course, you still need to do a lot of practice, but once you take away the basic concepts and equations and stuff from this video series, your journey onto calc will not be like hiking through a foggy forest where a lot of things are unclear. Instead, your journey will be a lot more clearer and easier. So let's begin. As legend says, it all starts with a falling apple. So one day, some random dude named Newton was sitting under a tree and an apple fell on his head. This made him wonder, why do things fall to the ground? And this later inspired him to discover gravity. But Newton isn't just known for discovering gravity, he was also known for inventing calculus. What Newton wanted for an experiment one day is to discover the instantaneous velocity of an apple falling down a tree. But back then, in Newton's time, people did not have devices to measure the velocity of an object. Yet, people did have rulers and clocks back then, so they can measure displacement and time. To clear up some things, we use the word displacement of the apple instead of distance traveled by the apple, because the apple is not only traveling a distance, but also in a downwards direction. And displacement includes both a distance and a direction. So in calc, we like to use the word displacement instead. Now let's say Newton collected the data of the displacement and time of the falling apple. Now he can put them in a table. Now as you can see here, the time points are listed in the first column, and we could call the time the independent variable. Then, as you see here in the second column, we have the displacement data listed, and displacement is depending on time, so it's called the dependent variable. The set of time points is called the definition domain, while the set of displacement data is called the range. The relationship is called mapping. Here we have a one-to-one mapping, which is, for example, when t equals 0.1 seconds, the displacement is 0.05 meters. This whole thing, this whole table is called a mathematical function, which includes a definition domain, range, and mapping. Let's look at another and more simpler example. Let's say you're driving a car at a constant velocity of 60 miles per hour. You can also build a table for this example with the measurement of time versus displacement. At t equals 1 hour, the car has traveled 60 miles, and at t equals 2 hours, the car has traveled 120 miles. A function can be represented in three different ways. The first way to represent a function is via a table, which is what we just did. There's the input and then output, and then the relationship, the mapping, etc. The second way to represent a function is via an equation. Ooh. Well, if we're lucky enough though. For our falling apple example, we're lucky enough to have a so-called analytical function. X equals 5 times t to the second power, which is a nice equation to represent the data. The equation is quite nice because it's like a simplified and general version of the data in the table, with an equation, you can plug in any input time into t, and you will get the right output, displacement, from x. The equation will basically process t into x. Now, the third way to represent a function is via a graph. The graph can graph out all the points from the table or equation and put them on a comprehensive image for people to see and observe. They say a picture is worth 1,000 words. That's why whenever we can talk about something using geometry, like shapes and graphs, we will do that. For the second example, you can also have an equation and graph to represent the function. The car is traveling at a constant of 60 miles per hour, so the equation is just x of t equals 60 times t. And we have the graph to graph out all the data for the equation, and you can see it's a straight line. This straight line right here. So now the question is how to find the instantaneous velocity at a specific point in time. To be honest, this is an extremely hard problem. All the way up to Newton's time, nobody knew how to solve that. But when Newton found a way to solve for the instantaneous velocity, he had invented calculus from there. So basically, to find the instantaneous velocity, you have to invent calculus. Okay, now let's go through the process of finding the instantaneous velocity. While we are doing this, think about if you could solve this problem just like Newton did. Well, first, let's start with calculating the average velocity, shall we? First, let's look at this graph of the falling apple example. Now I ask you, from 0 to 0.3 seconds, what is the average velocity? Well, we can use a formula that involves rise over run. Let me explain. So the change in displacement, 0.5 minus 0, the rise, divided by the change in time, 0.3 minus 0, the run. The result is the average velocity, 1.5 meters per second. So here's another example. What is the average velocity from 0 to 0.2 seconds? Well, you can use the same rise over run equation and get your average velocity for this case, which is 1 meters per second. Now, let's see just how this can help us find the instantaneous velocity. So you pick a time, t, this green point. So what is the instantaneous velocity at that time point? What is the instantaneous velocity at that time point? So to do that, we can use this green point as our starting point. Then we can find another time point later than our starting point. The x-axis difference, the time difference between these 2 points is called delta t. Then we can use the rise over run equation to calculate the average velocity between our current time point t and our next time point t plus delta t. Here's the thing, if I move this next time point closer to our current time point, the delta t, the x-axis difference between the 2 points, gets smaller. And yep, we can solve for another average velocity for this smaller time span. So here comes the leap of faith. If we keep moving the next time point closer to our current point and make the delta t smaller and smaller and smaller, the average velocity will get closer and closer and closer to the instantaneous velocity. Newton believed if delta t decreases to approach 0, then the average velocity will approach the instantaneous velocity. This very belief is what made Newton solve for the instantaneous velocity and thus invent the basis of calculus. Now, let's review all this math stuff with equations. So what we have here for the average velocity is the simple rise over run equation. Then for instantaneous velocity, we start off with the same thing, the velocity from time t to time t plus delta t. And this is equal to x of t plus delta t minus x of t divided by t plus delta t minus t. Rise over run. And according to Newton, when you let the delta t become infinitesimally small, approaching zero, you're limiting that delta t to zero. And then this x of t plus delta t minus x of t divided by t plus delta t minus t will become the instantaneous velocity, and that's our answer. Mathematicians like to be really very fancy and give very unique names to things. In physics, we know that the instantaneous velocity as the rate of change of xt, but in calc, we call the instantaneous velocity the derivative of xt with respect to t time. Oh yeah, recall that from geometry, for example, shapes can be used to let us understand something better. So are there any geometric meaning behind derivatives that could show us this in an easier way? Fortunately, there is. So let's look at this simple car example first. Here, the average and instantaneous velocity, aka derivative, are all equal. And from the graph, it is apparent that they are also equal to the slope of this straight line. So actually, the slope here is universal to represent the derivative for any linear function, and linear functions appear to be straight lines on the graph. Now with this hint, we ask a question. Is the slope for any point on a general function equal to the derivative at that point? Well, let's look at this example, the green point again. What is the slope at this point? Which is the same thing as asking, what is the slope of the tangent line going across our green point? Well, we use the same trick again. When we try to find the slope, we have to know the rise over the run. The run here is delta t. And the rise here is this little letter h. But we don't know what h is, so we cannot calculate the slope of the tangent line. However, we can use the average velocity to approximate the slope of the tangent line. The average velocity is expressed here, but when approximating the slope of the tangent line, there is an approximation error, which is this height between our blue dot and the tangent line. Let's call that extra height e. E for error. How do we improve the approximation? Well, we just pick a next dot, and the resulting average velocity becomes a better approximation of the slope of the tangent line. Because the e is smaller, the error is going down. Now, when we limit the delta t to 0, our approximation error will also approach 0. Now, you can see the average velocity will become the instantaneous velocity, and at the same time, the average velocity will be equal to the slope of the tangent line, and there you go. We have found out the geometric meaning of the derivative, which is the slope of the tangent line. So let's wrap this whole thingy up. For any function xt that is differentiable, meaning that you can find the derivative at any point on a function, its derivative will be equal to the rate of change or slope of xt for any t. Now, how about let's do a little review of what we just saw. In particular, for a straight line function, x of t equals at, its derivative equals to its slope a. and a is a constant, does not rely on t. Now, how about this quadratic function, x of t equals a t squared? And oh yeah, by the way, quadratic functions are functions that are second order polynomials. And recall that in school, we can graph out this function using a graphical calculator. So let me draw out this coordinate system. We got t and then x, and then once we use our calculator to find out the graph, and then there we go. Now let's find the derivative of this guy, which is limit delta t to 0 of x of t plus delta t minus x of t divided by t plus delta t minus t. This equals to limit delta t to 0 of a times t plus delta t squared minus a t squared over, oh yeah, t minus t is 0, so all we have left is delta t on the bottom. So we know that we have this little neat trick where if you have a plus b parentheses squared, you will get a squared plus 2ab plus b squared. So we can then find out what we will get when we take apart the parentheses. So we have a times t squared plus a times 2t delta t, this is all multiplication, plus a times delta t squared minus a t squared. And this is divided by delta t. Now, this is equal to limit of delta t to 0. So here's the thing. A t squared minus a t squared is 0. So that guy's out of the game. And now we can cancel out the delta t. So because this thing is over delta t, so this is gone, so this delta t is gone, and then this is like two delta t's multiplied together, and now we have only one delta t, and there we go. So for here, our final answer is 2 times a times t plus a times delta t. And then when we approach to 0, when we let delta t approach to 0, we get 2at plus a times 0. Delta t approaches to 0, and then a times 0 is 0. This is gone. So our final answer is 2at. There we go. So, and this thing, this 2 times a times t, can be used as an equation to solve for the slope at any point in t, which is pretty amazing. When t is 1, 2 times a times 1 equals 2a, and then the slope, which is the slope at t equals 1, and when t equals 2, well, 2 times a times 2 equals 4a, which is the slope at t equals 2. Now, let's sum up our key findings of differential calculus, which is just calculus about derivatives. And here's the best part. The best part is that we are already halfway through. Differential calculus is about half of all the core stuff for calc, so that's pretty good. Here's the summary. Our problem at hand is physics-based. it's a question asking about the velocity of a falling apple at a specific time. The instantaneous velocity is the rate of change of displacement with respect to time in physics. So you can see that is like really a physics question right there. Now we can use our imagination and let it help us think through the solution of turning the average velocity into the instantaneous velocity, which is what we want. The trick is to have the limit operation forcing the delta t to approach zero. And this is just a just discussed calculus-based calculation tool. And to top all of this off, there is a geometric meaning to the rate of change. It is the slope of the tangent line at the point we're trying to find the instantaneous velocity. So we have, for the falling apple example, the x of t displacement function graphed out. So let me graph this out. There we go. And then now it's complete. So then we can graph out its corresponding velocity function, vt, by like finding the slopes. So first we have the xt graph, and now we have vt equals 2at. And then that would be like this one. So you see here, for this point on the x curve, like let's say for this point, the slope is this guy, and that'll match up to this value on the VT graph. And then for this second point, the slope will be steeper, the slope value will be higher, and then you can obviously tell there's a higher value on the VT graph. And then for this point, the slope is even steeper. So on the VT graph, the value is going to be even higher. And yeah, here's the graph for every slope on the displacement function, which is the straight line to a t function. Oh, by the way, because delta t becomes infinitesimally small, we write it as a lowercase delta t, or dt. Well, and same thing for delta x, for the displacement difference. We write it as dx. And this is just a conventional thing to do in calc. We have dt dx. Now, we call this rate of change dx over dt, which equals to limit of delta t going to 0, delta x over delta t. This thing right here is called a derivative in calc terms. Okay, all of that from before was one half of the main portion of calc. What is the second half? Well, the funny thing is, it is actually all about the opposite of the stuff from the first half. That's right, there's a thing that is the opposite of derivatives. It is called the antiderivatives. The antiderivatives. So let's talk about these antiderivatives, aka integrals. So we know that vt is the derivative of xt. Then xt is the integral or antiderivative of vt. As long as we know the math to get vt equals 2at from xt equals at squared, like what we just did, it looks like we already know the answer to the integral problem. That is, the integral of vt is xt. But there's a thing we have to watch out for, the reverse problem, which is doing the integral. When we do the integral, we can actually have an infinite number of solutions. What? How does that work? Well, let me explain. If you look back to our little review with the at squared and all, you can find out that something like at squared plus c, where c is any constant, that is a real number, we can find out that at squared plus c's derivative is also 2at for any c. Alright, so the easiest way to show what I'm talking about here is using some geometry. Let's get out our at squared curve again. And we know its derivative is 2at. Okay, now, what if we look at this at squared plus c? Well, it will just be at squared shifted on c. Will the slope change? Nope. The slope will stay the same for any c. So the whole class of at squared plus c's derivatives are all 2at. All of these at squares plus c's derivatives, okay, they'll all be the same thing, which is really crazy, but here we have it. It's a true thing. Their slopes are all the same. So as a result, the integral of 2at is at squared plus c, and c is any constant, which is any real number. Now, we can also find this situation out from physics. So let's go back to our falling apple example. We have xt equals at squared and vt equals 2at. Now, what if we have another coordinate system where the origin is higher and our starting point of our apple is now this C? Then you will just have this new coordinate system as shown here, where xt equals at squared plus c. How about velocity? Well, here's the thing. The whole experiment in reality has not changed at all. The tree was not shorter, the apple did not start falling elsewhere, everything is exactly the same. We just used another coordinate system to measure the apple falling. So the velocity is still the same from before. It does not matter where the starting point of the displacement of the apple is. Now, you see here the derivatives of the displacements are the same regardless of c. That is what I mean when you do integrals, you might end up with infinite solutions. If you want a specific solution, you have to have like a fixed initial condition. Like, the best thing to do is just let c equal to 0. Like, just set your origin to 0, which is the neatest and most convenient thing you can do. Okay, now we learned what integrals are and their basics, let's talk about their geometrical meaning. Yep, like derivatives, integrals also have some geometricness to them. We know that the geometric meaning of derivatives are slopes. Now, let's try to find out what the geometric meaning of integrals are. So let's revisit our 60 miles per hour car example. So this car is moving at a constant 60 miles per hour. The velocity isn't changing in any time. So this vt velocity graph's curve is this straight horizontal line. Now let's draw out this xt graph. Xt equals 60 times t. Okay, now let's pick out a random time t. Let's call it t0. So on the xt graph, when t is t0, xt equals 60 times t0. And as you can see on the vt graph, there is the t0 again at this point. And wait a second. So when t is t0, xt is 60 times t0. And I just realized that this area under the curve of vt all the way up to t0, this area under the curve looks like a rectangle. Its area is this length t0 times width, 60. The area is 60 times t0. Now that is the whole kicker to this thing. The integral is just the area under the function. Well, at least for this example. Let's try another example. So once again, we pick a t0, and then on x of t, when t equals t0, xt equals a times t0 squared. And then on this vt, you also have this t0, and hold on a minute, this area under the curve is a triangle. And when t equals t0, by the way, for vt will equal to 2a t0. So to find the area of this triangle, it is going to be the base t0 times height 2a t0. Oh yeah, this here is t0. And then back to the area, t0 times 2a t0 times a half. Base times height times a half. That is the area of a triangle. And the 2 and a half can cancel out. And then it will be t0 times a t0. And then our answer is a times t0 squared. Bam! We once again saw that the integral is just the area under the curve. And that is the geometrical meaning of the integral. Now, here's the tricky part. Sometimes the area under the curve is hard to solve. It may not be a rectangle or a triangle shape. It could be this curved and odd shape sometimes. So, what is the solution to this? Well, the solution is to divide this area under the curve into these little intervals, these little rectangles. And yeah, the width of each of these little rectangles is delta t, and it's going to be the same for all of them. So now what you do next is you let delta t approach 0. You limit delta t to 0. And as you can see here, when the delta t gets smaller and smaller, the rectangles get thinner and thinner, and then they match the curve better. And then when delta t approaches 0, the rectangles will become so thin that they will exactly fit the curve. Then what you do next is that you add up all these little intervals together, you add up all these little areas together to get the area under the curve. So there's an equation to solve this. So the solution is you limit delta t to 0 of sigma n equals 0 to n minus 1 of x times n delta t of delta t. Oh yeah. Don't worry if you don't understand this equation yet. The purpose of this video is to just give you a little introduction to calculus. Just to show you a basic idea of calc. So now for some more info. So to find the integral, you have to know the area under the curve. What if sometimes this area under the curve is under the x-axis? Well, this is where the funny part happens. This area right here is actually a negative area. So when you add these two areas up, you actually have to subtract this one from this one. So let's do another example. So we have a function right here. These two areas are positive and this one is negative. So what you do is you add up these two areas and then subtract this area to get your integral. All right, now let's summarize the key findings of integral calculus, which is calculus about integrals. 1, we know that the problem we are trying to solve, finding the displacement from velocity, is physics-based. And oh yeah, by the way, displacement is also called the anti-rate of change. 2, the geometric meaning of the integral is the area under the curve. And 3, we know that the sum of very thin slices of an area under the curve can approximate the real area, and we can make those thin slices infinitesimally thin to a point where their sum can equal and represent the true area. This is the calculation tool for the integral of general functions. And the above calculation involves summation and limit operations, which leads to the math formula for integral, which is this big S symbol to indicate the summative nature of the integral. You're adding up all those little rectangles together. Again, the integral is the opposite of a derivative. Mathematically, it is the antiderivative. Okay, why? Just why do we need to learn any of this? How is this useful? Well, it's because that all the jobs in STEM, science, tech, engineering, and math, like being a biologist, a chemist, or even a robotics engineer, all of these require calc. Calc is the reason why we even have modern tech like phones, cars, and airplanes. So there's going to be a lot of useful applications that is related to calc. There are so many applications for calc. For example, calc is really useful for optimization, like finding the maximum or minimum of stuff. So let's say, for example, you threw a baseball. It reaches its highest point at some time and then it falls back down to the ground. So you want to know when the baseball reaches its maximum height and what is its maximum height. So all you have to do is have a coordinate plane, and then this is t time, and this is x of t displacement, and then you can find like the t and xt, and there's a trick for that. All you need to do is find the time when the slope is 0, because at this time when the baseball reaches its maximum height, the slope is 0. So all you have to do is find the derivative, let dx dt, the derivative, equal to 0, and then find things from there. Calculus is also very useful for physics. In physics, there's a basic formula that you need to know. Force equals mass times acceleration. And guess what? Acceleration is the derivative of velocity, d of vt dt. And you can also use exponential functions or logistic functions to model concentrations of different chemicals in an reaction for chemistry. And those functions are actually solutions of equations related to derivatives. In biology, you can use exponential growth functions as well to see the population growth of cells and bacteria. In electrical engineering, the electrical current equals the derivative or rate of change of electrical charge with respect to time. And in robotics uses electrical engineering and physics, and at there you use differential equations that characterize the conservation of momentum when robots collide. You got stuff like momentum and velocity. So, how do you feel now? Is calc hard or easy? Believe me, for many people, it is hard. But if you're done watching this video and feel like things at least cleared up to some extent, then things are going to be so much clearer in the future as you just got an intro to calc. Yes, there will be a lot more to this in this video series. In-depth coverages will be continued, peculiarities will be revealed, subtleties will be mastered, and eventually this series is going to help you clear up concepts, list down important must-know facts, and basically give you the right tools for both passing calc and excelling in STEM and helping your career. So yeah, I hope you enjoyed this video, guys. See you in the next video.